talking about the first derivative test. What the first derivative test tells us, it tells us two things about the actual function. So the f prime test, or the first derivative test, tells us where f is increasing or decreasing and where f has local mins and maxes. Well, I'm just going to say local min and max because I don't like the way this words look. So this is what the f prime test tells us. I'm going to have a step-by-step process that, of course, you should include on your formula sheet because it's a lot to remember, right? And of course, you should have example problems on your formula sheet, right? And the main thing is the conclusion. The conclusion is the most important thing that you give me, okay? So first of all, let's talk about the increasing, decreasing piece. The first derivative test says if f prime of x is greater than 0, positive, right? If f prime of x is positive, then f of x is increasing. And we're going to cheat this a little bit. We're going to think about it backward. We're going to say, oh, look where the function's increasing. I better be able to show that my derivative there is positive, right? So for example, y equals x cubed, right? Take a look at that curve, right? Of course, we know this. So there's my curve, and if I draw a bunch of tangent lines on it, look at that tangent line, look at that tangent line, look at that tangent line. Notice they're all positive. They all have positive slopes, right? You with me there? Right? So I can tell what the calculus is before I even do the calculus. Yes? I can tell what the calculus is, and this is why calculus is so easy and so natural to all of us, and why we've been torturing you with algebra for your entire mathematical life. Everything we've been doing is so you can do the algebra that you need to know when you get into calculus. And so if I look at y prime, what do I get? 3x squared. No matter what x I put in there, what's the value? Positive. If I put a negative in there, it's positive, right? The only weird place where I put where it's not positive is at what value? 0. So, and there could be a local min or max there. It's a critical value of the derivative, right? In this case, it doesn't happen to be. There is no horizontal tangent line there. You can kind of see it in the graph, right? So that's my increasing piece. What about my decreasing piece? Well, you already know, right? Because your gut instincts are right. As humans, we're pretty good at picking up patterns. So decreasing, right, piece says if f prime of x is negative, right, then f of x is decreasing. So interesting piece there, or one of these mother functions that we've known for a very long time is 1 over x curve, right? So this is y equals 1 over x, yes? Look at it from left to right. Whenever we're talking about increasing, decreasing, we have to work left to right. So do you see it's always decreasing on that left part of the curve? Yeah, and always decreasing on the right part of the curve, right? And look at the derivative. Who's got it for me? Beautiful. Negative 1 over x squared. Notice x squared is always positive, but there's a coefficient that's a negative 1, so it's always going to be negative. When my derivative is negative, the function must be decreasing. What's the critical value of the derivative? 0. But does 0 exist on the graph? When x is 0, is there a point on the graph? No, so that critical value is useless. There's no point on the graph there, right? So we've talked about increasing, decreasing. We need to talk about the local mins and maxes, right? If f prime of x equals 0, and f of x is defined if f prime of x changes signs from positive to negative. Remember I told you how much of a headache this chapter was? Are you believing me now? Because wait till you see we even do a problem. I'm just telling you what we're going to be doing. I haven't done a problem yet. And it's taken forever, right? If f prime of x changes signs from positive to negative, right? Think about it. From positive derivatives to negative derivatives, what's going to happen at that critical value? I'm going to have, right, c comma f of c is a local max. Right? Do you see that? You get that idea? I need the point to exist. I need the derivative to change signs. If it changes from positive to negative, right, positive slopes to negative slopes, then I know I'm at the top of a hill. What happens if it changes from negative to positive? Local min. I don't have to write it, right? You agree I don't have to write it, or do you want me to write it? Do I have to write it? No, okay. All right, here we go. Let's do a first derivative test. Now I could ask for 3 things when I ask for a first derivative test. I could tell you, just tell me where the function is increasing or decreasing. Just tell me where the local mins or maxes are, or the whole thing. Do the whole first derivative test. I usually do it in pieces on the exams and quizzes because it's a lot to do. All right? But let's do a whole derivative first. So I'm going to use, I need to give you step by step, sorry. Step by step for the f prime test, for the first derivative test. Step 1, graph the function. And notice everything that you're looking for. Notice where it's increasing. Notice where it's decreasing. Notice where there are local mins. Notice where there are local maxes, right? Yes, you with me? Good. Step 2, find f prime and the critical values. I usually call these guys C1 values. C meaning critical, 1 meaning first derivative test. Does that make sense? Because I'm going to need critical values for my second derivative, and I'll call those, what do you think? C2 values, right? So there are critical values of the original function as well, where the original function is undefined, where the original function hits a 0, right? So talking about the domain and the roots. So when we go first derivative test, we're talking about, I call them C1 values. When we do second derivative test, I call them C2 values. In Calc 2, you'll find a fourth derivative or something. So step 3 of our step-by-step. Do you remember doing sign tables in pre-calculus? Do you remember doing sign tables? And thank you, Sina, for saying everything I say in pre-calculus And I know she's she said, oh, I better shake my head. You remember doing sine tables? You had to figure out what you would put test values in, and you'd have a table of pluses and minuses, and you'd figure out where the function was above the x-axis or below the x-axis. Remember, and how horrible they were? I will tell you, it wasn't that bad. Well, these are a lot easier. The way we're going to do them in calculus is a lot easier. So we're going to do a sine table with a number line. Step 4, we're going to do test values, but we're going to cheat it. So I guess test values is a part of the sine table, so really not right. I'll just say step 3, sine table with a number line, and you're going to cheat the test values. Come on, pen. Cheat the test values. You're in calculus. I don't care. I know you already know how to plug a number into a function, right? I know you know how to do that. Why are we going to waste our time doing that? Step 4, conclusion. And remember what the conclusion can be. If f prime of x is positive, the original function's increasing. I already wrote all this, so I'm not going to write it in step 4. If f prime of x is negative, the function's decreasing. If f prime of x is 0, and that point exists on the original graph, and the derivative changes signs from positive to negative, I have a local max. From negative to positive, I have a local min. I need all of that in my conclusion. Okay? Nice, here we go. Oh, I know which problem. I don't need the book. I remember which problem I want to do. So this is an example problem of the f prime test. And we're going to have the function x squared ln of x. So it's a pretty interesting curve. Of course, what's my domain here? Zero to where? Infinity. Does it include 0? No, right? Because I can't plug 0 into ln, right? So hopefully you've graphed it already. Here it is. So I've open hole at 0, 0, right? What's the x intercept there? You have it graphed on your calculator, you can just look at it. You have Desmos open, just look at it. Are you shopping? What are you doing? The height is 0. What's the x value? Well, how about this? When is ln equal to 0? When is ln of x equal to 0? 1, thank you. So this is the point 1, 0, right? And this is 0, 0. Of course, we can see that the function is doing what to begin? Decreasing, right? So the derivative should be negative there. And then it hits a local min, right? Yes? It's also the absolute min, but we always call them local mins. Right? 4.2, we're caring about absolute mins and maxes. 4.3, we're calling everything locals. And then it starts increasing again. Right? And that point down there does exist. Do you agree? There's no hole in the graph there, right? Okay. So we know the whole first derivative test just by graphing this thing. We also know our number line is going to look like this, right, from 0 to infinity when we do our sine table. I have to think of the domain of the function when I do the first derivative test. Okay, step 2, find the derivative, find the criticals. On your mark, get set, go. Anybody get there? Go ahead, I'll give you another minute or so. Nice. Good, find the criticals. If you've got the derivative, find the criticals. Roger, you get the derivative? Nice. We have 2 criticals for this. One of them is useless, right? So my critical values come from f prime of x equal to 0. There's no denominator, so I don't have to check for it being undefined, right? Which means x equals 0 or 1 plus 2 ln of x equals 0. This one is no good. Why? Not in the domain, right? Not in the domain, so I have to, I need my first derivative criticals to be in the domain. The second derivative criticals don't have to be in the domain. But my first critical derivatives do, and I'll explain that later, but so what do I get for the second one? I get ln of x equals negative 1/2. Is that agreeable with everybody? And then I raise both sides to base what? E. So I get e to the ln of x should be e to the minus 1/2. On the left-hand side, e and ln are inverse functions, so they cancel each other out. I get x equals 1 over the square root of e. For my own sanity, I will get a decimal for that, right? Just for my own sanity, I might be able to think a little bit better if I know what decimal that is. 1 divided by second square root of second e. It's about 0.6. So when I'm doing test values, I want a value smaller than that. I need when I do, remember a sign table, you have to test left of, right of, and in between all your criticals, right? I only have one critical, so I'm going to have to get a number less than that and a number right of that for my test values. Just so you notice that 1 over e and e, well, e is 2.7 something, and 1 over e is 0.37. So those are good test values for me. Do you see that? Okay, here's my sign table. I know I'm using a number line now as my sign table, and I want to partition it with the criticals, right? So the only critical I got was 1 over the square root of e. And I want to test values left of, right of, and in between all my criticals. So I'm going to test 1 over e and e. When I'm testing trigs, I want to use some kind of pi's, right? When I'm testing algebraic, I want to use some kind of easy real numbers. When I'm using an ln, I want to use powers of e, right? Because it's easy to evaluate. Yes, you with me? Now, I don't feel like plugging these in. I will plug one in for you so you can see it, but I'd rather just cheat. I'd rather say, hey, look at the function. It's decreasing at first. So that means my second derivative, right? So I'm sorry, my first derivative, f prime of 1 over e, had better be negative. I am testing the second derivative. So I'm plugging test values into my, I'm testing the first derivative. So I'm plugging my values into the first derivative. And over here, f of e must be positive. So you see how much easier that sign table is compared to pre-cal? I don't know why you're all not nodding madly at me how much that sign table in pre-cal was a pain in the everything. So this is how we do them now. Just so you watch me test, right? That's f prime. So f prime, what did I get? F prime of e was e times 1 plus, it was, 1 plus 2 ln of e, right? And that's e times 1 plus 2, because ln of e is 1, so I get 3e. So positive, yes? Positive. So, but we're in calculus. I don't need you to show me this step. Does that make sense, what I'm saying there? But now I want the conclusion, and I want the full conclusion, and I want a shortcut conclusion. I don't want you to point at the graph and say, see? I want you to write out the conclusion. And that's typically where students lose points on these types of problems. They don't give me a conclusion. So what good is it without some kind of summary of what the hell's going on, right? So conclusion. Since f prime of x is negative on 0 to 1 over square root of e, f must be decreasing on the same interval. And those intervals are always open. They're always open intervals. Remember in pre-cal how we did everything in intervals, right? So we'd always say that the function is greater than 0 on this interval, or the function is less than 0 on this interval, right? Since f prime of x is positive on the interval, and I'm just doing this a couple of different ways every time I do one so you can see you have options. On the interval I equal to 1 over square root of e, comma, infinity, f must be increasing on I. Right? Go to all my chapter 4 tests, go to all my final exams, read and practice every single problem on the first derivative test, every single problem on the second derivative test. Since f prime changes signs from negative to positive at x equals 1 over square root of e, and f of 1 over square root of e, which equals, right, it was x squared ln of x, right? What is that? E times negative 1/2, negative 1 over 2e exists. Right? Remember, I needed the derivative to change signs, and I need the point to exist. Yes? If the point doesn't exist, it can't be the top of a hill or the bottom of a valley. Yes, you with me there? Somebody nod, please, or grunt. Thank you. Since f prime changes signs from negative to positive, and the point where it changes exists on the original function, right? 1 over square root of e, comma, negative 1 over 2e must be a local min. Bang. Done. If there's no interval where the function's decreasing, then you don't have to mention it. If there's no local max, you don't have to mention it, right? Does that make sense? Everything that you find, mention in the conclusion. What's the trickiest part about this last third of my conclusion? Probably finding the height of that min, right? Especially if you didn't have pre-cal, it's not easy to, right? It's not easy to find that value. It's not easy to see 1 over the square root of e is negative, ln of the 1 over the square root of e is negative 1/2, is it? Is it? It should be easy. Why is it negative 1/2? Because ln and e cancel each other out, and what was the exponent? Negative 1/2. Nice, that's my first derivative test. There's plenty of problems for you to practice. Sometimes you won't have increasing, sometimes you won't have decreasing, sometimes you'll have several intervals and you're going to join them with a union. Sometimes you won't have any local mins or maxes, right? Like the one we did at the beginning. Am I okay to change this page? Or yeah? The one we did at the beginning, right? Y equals x cubed. Right? Y prime is 3x squared. C is equal to 0. You agree with me? Critical value there is 0. Yes? But if I look at my number line test, right, I see that the first derivative is positive to the left of 0 and positive to the right of 0. So why don't I have a local min or max there? The derivative doesn't change signs. The derivative must change signs. Nice. Let me stop this recording. That's a first derivative test recording.